A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear students, today our theorem is if fx is bounded and measurable on E, then fx absolute is Lebesgue integrable on E. Conversely, if fx absolute is bounded and measurable on E, then fx is Lebesgue integrable on E. Let us suppose that fx is bounded and measurable on E. Then we are to prove that fx absolute is Lebesgue integrable on E. Since fx is bounded, so fx absolute is also bounded. Similarly, since fx is measurable on E, so fx absolute is also measurable on E. Thus, fx absolute is bounded and measurable on E. Now, let us take an arbitrary partition set y0, comma y1, comma dash 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 yn. As usual, we choose ek, the set x belong to E, such that fx absolute is greater or equal to yk minus 1 and less than yk. Now taking the upper sum, that is capital S is equal to summation k is equal to 1 up to n yk m of ek, and the lower sum small s is equal to summation k is equal to 1 up to n yk minus 1 m of ek. This implies that capital S minus small s is equal to summation k is equal to 1 up to n yk minus 1 m of ek. Call this is equation number star. Since fx absolute is bounded on E, so for every pre-assigned epsilon greater than 0, we can find a partition such that yk minus 1 is less than epsilon divided by m ek. Thus, the star becomes capital S minus small s is less than summation k is equal to 1 up to n epsilon by m of ek. This is equal to epsilon by m of ek is taking out from the summation and taking over the summation k is equal to 1 up to n m of ek. Now we know that summation k is equal to 1 up to n m of ek will gives us the whole domain which is E, that is m of E. So epsilon by m of E dot m of E will cancel out, so remaining is epsilon. This implies that capital S minus small s is less than epsilon. Now we know a result which states that a function fx is Lebesgue integrable on E if and only if for every epsilon there exists a partition such that capital S minus small s is less than epsilon. According to this result, we at once notice that fx absolute is Lebesgue integrable on E. Conversely, let fx absolute is bounded and measurable on E, then we have to prove that fx is Lebesgue integrable on E. Now since fx absolute is bounded and measurable on E, so it is Lebesgue integrable on E. Thus, it means that integration on E fx absolute dx exists. It means that its value exists, but we know that fx absolute is equal to plus minus fx. So integration on E plus minus fx dx exists. So integration on E fx dx and integration on E minus fx dx also exist. This implies that fx and minus fx are Lebesgue integrable. Thus fx is Lebesgue integrable on E, which completes the required proof. Now we have next theorem. If fx is bounded and measurable on E, then prove that integration on E fx dx absolute is less than or equal to integration on E fx absolute dx. Proof. We know that fx is greater or equal to minus fx absolute and less than or equal to fx absolute. Taking over the integration, this implies that minus integration on E fx absolute dx is less than or equal to integration on E fx dx less than or equal to integration on E fx absolute dx. Now let's suppose we take integration on E fx absolute dx is equal to alpha and integration on E fx dx is equal to beta. Then from the above result, beta is greater or equal to minus alpha and less than or equal to alpha is less than or equal to alpha. This implies that beta is greater or equal to minus alpha and less than or equal to alpha, this implies that beta absolute is less than alpha. So this implies that the value of beta is integration on e fx dx whole absolute, and the value of alpha is integration on e fx absolute dx. Here on left side absolute is on the whole, and on right side absolute is only on the function. It means that the integration of the absolute of the function value is greater than the whole absolute.